Okay. Welcome, everyone. I would like if someone can tap okay or yes if you can hear me. I can't see anyone. Do you guys hear me? Yeah. Okay. So the plan for today is to finish the what we were talking about last time about conservative vector fields and line integrals that are independent of path, and then finish Green's theorem, and then uh, we'll start talking about triple integrals. Okay, that was the last meeting. Now today. So I will recall what we were doing, briefly speaking, because I can understand that sometimes we don't. These concepts are a bit more, for the first time, it's a bit more abstract than just calculations. Okay, so we did speak about line integrals. Okay, so line integrals are just there are two types of line integrals. There are those with a ds and those with a dx and dy. Okay, where is it? So those with the ds, I know I just remembered that we didn't speak about applications of this ds. So let me just start with this. Let me go back a little bit. Yeah, I think I will just go back to. So what I will do is this was supposed to be. Mhm. I'll start a new notebook. Okay, and then we'll. Okay, we'll catch up. So applications, but it's very easy as you can see. So this is supposed to be right after we talked about line integrals of ds, applications of line integrals. There isn't that much. I mean, the most important one is the one you already know about. Uh, Remember what we were talking about, the center of mass and the mass and all of that. So line integrals that allow us to do the same thing, but not for the regions that are in 2D, but they allow us to do the same thing for wires that are like, for example, if I have a semicircle, okay, let's say semicircle, okay, and this is like a wire that is bent so that it has a shape of a semicircle. Okay, let's say that this is a circle. Just to fix the ideas, x squared plus y squared is some a squared. Okay, and the material is not uniformly distributed on this wire because the density of mass that will depend on x and y will be some function of x and y. Okay, so a certain amount of, it's a function of gram per unit, right? Because it's still a length, right? It's per unit. In the case of 2D, remember it was something of like, if it's a mass density, then it was like a gram per unit square, and it's an instantaneous um, function, which means that it's evaluated at a point, not a it's not uniform throughout the region. So when you have such a function, right? So you want to see what is the total mass, right? So you do the same thing. What you do is you divide this wire into little pieces that you're gonna call them ds, okay? And then for each ds, you suppose that the function doesn't vary that much throughout the ds. So what you get is you have xy ds, and then you have to add all of these. So you have to integrate over all the curve. Okay, this is the curve, right? And then the same formula applies. You just have to plug in what we did yesterday. This is just square root of x prime t squared plus y prime t squared dt. Okay, and then you integrate over all the okay, and the center of mass is okay. So this is the total mass, and center of mass is given by, well, it's the same thing actually as in the 2D, right? You have to, for each little tiny sub arc, you have to, what is the distance from the x-axis and what is the distance from the y-axis, okay? So this is the y-axis and this is the x-axis. So what you do is this little piece, it has a mass that is xy ds, and the whole thing, right? So this is the mass of this little piece, and the whole thing is distant from the y-axis by a distance x, right? And then you have to do it for all these little pieces. So you integrate over all c, and then by the end you have to divide by m, kind of normalization, and then this gives you x bar. Okay, and then the same thing applies for y bar. You have to integrate y bar over y whole xy ds over the circle c, and then you divide by m. It's really applied formula. I mean, if you know how to do a line integral, you just apply the formula, and and you apply it for every kind of curves. And you say, if it's a circle, if it's a line that is like this, or curve, anything, you just apply the formula. What we need is just the curve. That's all. It's just the curve and the function here. And don't forget to apply the functions on the curve, which means that you plug in what is x and what is y in the curve. Okay, so I don't think I'll do an example, but I just wanted to make sure that you understand. But you will see the same idea will come over and over again. See, for example, we did it for 2D, and now we do it for 1D, but for curves. But it's the same thing applies for 3D. If you have a solid, as we will see today, if you have a solid, then you apply the same thing. It's going to be a function of three variables that gives you how many grams you have per unit cube, right? And it varies throughout the solid, and then you have to multiply by the small amount of volumes and integrate over all the volume, and then you have to, for each of these little cubes, you multiply by x, multiply by y, multiply by z, and then you do a triple integral, as you will see, and you divide by the mass. You divide by the mass, it gives you x bar, y bar, z bar. See? Same thing. So make sure you understand this, or at least just remember the formula, because it's part of what you're supposed to know. Okay, so that was a little digression. Okay, so I told you how to do these line integrals. So it's really basically a line. If you know how to do this, you know how to compute the mass and the center of mass. So I told you how to compute this. We did an example, right? And then I introduced you to another type of line integrals, which are, now you don't apply it to ds, which is a little arc, but you apply it for the associated dx. See, for example, you take a little ds and you see how much you are varying in the x-axis and then how much you're varying in the y-axis. So because now this is a length, this is never negative. Now this one can be positive and can be negative. That's why that's why if it's a positive function, one is going to give you always positive thing, and this one can be negative. See, for example, here the dy is negative, and here the x is positive. See, if you go in on the other direction of the curve, ds is still positive, but ds is still positive because you have always to give an orientation for c. Now ds is gonna still be positive because it's square root of something square plus square square, right? Which makes sense because it's a length. After all, it's supposed to be positive. But dx now will be on the other direction. You're moving along the other direction, so it's going to be positive, and y will be positive. Yeah, dx will be negative, and the dy will be positive. Okay, so these line integrals, they look like, when they tell you compute this, you have to compute this, and you have to compute this. And I told you how to compute these type of integrals. You just have to write down the curve and do this dx, dt, and right? You have to compute the derivative with respect to t, and this is a way to remember the formula. Right? You plug in, and you are supposed to have everything expressed as a function of t by the end of the day. And the boundaries are always those boundaries that give you the curve, because the curve is parameterized by t. And then we talked about, if you have a field, a vector field, we can define the work of this field, right? From a line, and this one is constant. And then we applied the same thing for a curve, but the function is also allowed to vary. The vector field is also allowed to vary throughout the curve. Now, what we did is we applied the same formula, the same high school formula, to each little curve, to each little polygon we have, and we just did the approximation that because this is very small, the function doesn't vary that much, the vector field doesn't vary that much, and it can be approximated by this direction can be approximated by the direction of the tangent vector. And then the function doesn't vary that much. So we apply this momentarily, and we did the sum over the curve. And then we did some calculations, and then we realized that a way to compute this work is you have to take f, the vector field evaluated at the curve, take the scalar product with the derivative of r. Sorry, here it's r. Take the scalar product, and then this is going to give you some scalar function that depends on t. Then you integrate from a to b, where a, b are the boundaries of the curve. And we did an example. I didn't do the whole example, but I did one path, and we realized that what we didn't realize. I mean, I told you that if you do it on the other side, it'll give you another number. So for one path, it gives 5/2, and for one path it gives 2, and for the other one it gives 2 minus pi/2. And of course, minus pi/2 is not 0. So we realize that the work done by a vector field depends on the path you take from a point to another one. And then we talked about fundamental of theorem of line integrals. Then we took a vector field, a very special vector field, which is the gradient of a function of two variables. We did the calculation for the work done by this vector field from along a curve from A to B, and we realized that it doesn't actually care about the form of the line. It actually only cares about where you end and where you start. So we realized that this does not depend on a curve. So we introduced the concept of independence of path, which means that a line integral does not depend on the curve you take from a point to another one. And we call, of course, and conservative vector fields are those who have the form of a gradient. And then we realized that a vector field, the line integral, is path independent if and only if for every loop you take, it gives you 0. It's not always the case that it gives you 0, but it gives you 0. And then, well, that's the proof. Okay, and then we introduced these open connected regions, and we realized, I told you that for this type of regions, if you have a vector field defined on this type of regions, then the only path independent vector fields are those who are conservative, right? There's only one type of path independent vector field. It always comes from a function of two variables, only if it's open and connected. And now we started talking about, okay, I give you a vector field, is it conservative or not? Which means that, does it come from a function of two variables? We realize that one direction, I mean, if this is true, then we must have that. If the vector field is given by this P and Q, where P and Q are two nice functions with continuous partial derivatives, we realize that if it's conservative, then this must be true, okay? And now we start talking, is this, so it's necessary, it's a necessary condition for a vector field to be conservative, but is it sufficient? Which means that if I have it, can I conclude that it's conservative? The answer is no, and I will say an exercise, well, no, right? There is an exercise that says that this is true, but it's not conservative. But for certain kind of regions, namely regions that have no hole and they are open, this is true. So here is the theorem. So the theorem says, let F be a vector field defined on an open, simply connected region D, okay, with P, Q having continuous first then del P del Y implies that F is conservative. Okay. So the proof of this theorem will, let me see. So the proof of this theorem, we'll do the proof, or I will maybe just outline the proof in the exercises, but it'll follow from Green's theorem that we'll see. Sorry about that. So this proof will follow. So why does it work? You will see that it will follows it follows from Green's theorem. See you later. We'll see Green's theorems in a moment. But let's just do an example to see how it works. Consider the line integral over C of sine y dx plus x cos y minus sine y dy. Okay? Where C is some curve, is some path from so when you see these kind of questions, don't try to compute it with the formula because you don't actually have the curve. I don't give you the curve. So you must be aware that if I don't give you the curve, right? So it doesn't depend, like right? If I don't give you the curve and I tell you evaluate it, you can tell me, okay, which curve? Well, if I'm giving you this, it's because it doesn't depend on the curve. So what you do is you need to show that, let us show, let me call this one L, that L does not depend on the path C. Okay, so how you do that? Well, use the theorem, but you have to make sure that you have to make sure that the theorem applies, which means that the region you're applying your theorem to, it has no hole and it's open. But in general, it's not going to be that hard. You apply it, So apply let me call this one 2. Let me call it conservative test. Apply conservative theorem to the region. You have to give the region, because if the region has holes, you cannot apply it. To the region R3, R2, you know, or some big circle that contains your, you know, see, because what you want to show is, uh, you want to show if it's conservative. So it might, you need conservative where, right? A field is always defined somewhere, right? If I'm giving you this field, so it's uh, conserved the region R2, and the field F given by sine y plus, yeah. I didn't say that, but you must realize that if if you have a vector field, if you just apply the formula, you will realize that this dr, right, is the same thing as d dx, because dx is r prime dt plus q dy, where f is given by p I plus q j, right? Just apply the formula and you'll realize it's the same thing. So if we apply the field, we apply the theorem. So this is a vector field. It's defined everywhere. These two functions, they have no problem, and they are defined on the region R2, and R2, luckily enough, it's open, right? And if you give you a point, you can find a ball that is still inside the plane, and it's simply connected. I mean, R2 does not have holes, right? Uh, the plane does not have holes. So the theorem applies. Theorem applies. Now we check. What is the check? What is dy of p, right? Because remember, it's dy of p, right? So this is p, and this is q. What is dy of p? It's cos of y. And what is dx of q? Well, it's cos y minus 0, which is cos y. So they are equal. So this is true. Hence, f is conservative. Conservative. But be aware that it has, the region needs to have no hole, right? You cannot just say, okay, I have this, then it's conservative. F is conservative. Okay, so what does it mean? It means that f is the gradient of a function f. And okay, but this does not solve the problem because you want to evaluate the integral c. And if you want to evaluate the integral c, you need to find f. So to evaluate L, we need to find f of xy. Okay? Well, unless you really want to go to the proof and do it, but there is no magical spell. So it'll give you f. You have to do it by hand. So it's like linear systems of equations. So we need fx such that dx dy gives fx and dy gives fy, which is cos x, which is sine of y. And here it's cos y x minus sine y. Okay? So these are the system you have to solve, right? And that's actually, well, that's actually pretty much what I was doing actually when I was doing my master's. It seems a bit easy, but a lot of calculations I was doing in my master's were like this. I was like, okay, find f such that this is true, and then I had to torture myself to find all of these constants because as you'll see, you will be adding a lot of constants here. See, so you're already doing some real mathematics here. Okay. Uh, okay, so what does this first equation gives? One gives so okay, so it's a function of two variables, but then y is fixed, right? And you have a function of two variables. When you take the partial derivative with x, it gives you sine y. So what is gives you integrate? So fxy, because now y is fixed, right? It's a function when you fix y, right? So what gives this? X sine y plus hy or some function hy of y. Because this is now a constant, right? The most general constant, right? If you have a function of two variables and we take the partial derivative, now we fix y and you take the partial derivative with x, which means that you're basically it's a function of one variable. So you integrate the antiderivative. What's the function that gives you this? Right? Now, applying to, okay, apply, okay. apply del y to fx and use 2. So del y del fx. So we have two things. So when I apply it to f, it gives del y x sine y plus hy, which is x cos y plus h prime. Okay, I'm going to change the color, which is equal, this is by 2, which is equal to x cos y minus sine y. Okay, so h prime of y is equal to minus sine y, which means that hy is cos y plus a constant. Now it's a one variable function where c is a constant, right? Now you can choose whatever you want. We can choose, we can choose, we can choose, you can keep it c, right? It's not a problem. We can choose c equal to 0. So f x y is equal to x sine y plus cos of y. Okay, and now you can check that. So you can always check and make sure that you didn't do any error. Check that the gradient of f is equal to f. So by the fundamental theorem of line integrals, we have that the integral of sine y dx plus x cos y minus sine y dy on c is the same thing as the integral over c of vector field f vr, which is the same thing as the integral of the gradient of f times dr of c, which is the same thing as f evaluated at the point 1 pi. Remember, we had 2 points, right? It's the point 1 pi. That's the end point, and that's the starting point. Okay, minus f of 2, 0. So this is by fundamental theorem of line integrals. Okay. Okay, so f is 1 sine pi plus cos pi minus 2 sine of 0 plus cos of 0. right? Because this is s, x sine y cos y. So if it's 2, 0, 0, and 1 pi pi, and this is equal to -1 minus 1, which is -2. Okay. Do I have any question here? Okay, let's do another example. Another kind of example. Example is the vector field fx conservative. Okay, the vector field defined on R3, on R2. So again, R2 is open and simply connected and P and Q are C1, which means that continuous first order partial derivative. I mean, this will almost all the cases will be like this. These are two polynomials. When you take the partial derivative, the first one is it's 1 and -1, and the other one is 1 and 0. So okay, so here what you do is don't try to test it on every possible curve, because you cannot do it. I mean, even a computer cannot do it. So let's see. You have to apply the theorem. So by this conservative test, I call it conservative test. No, this is not something. Don't do it. Don't. Yeah, I think I should be careful when I do this. Don't use this in the assignments, or at least make sure that you say something else, because the TAs maybe will not understand what you're saying if you say the C, because I will not grade the assignments. The TA will grade them. So if you say CT, you say, okay, what is CT? You have to say by the test or by the theorem, or what you have seen in class, or by theorem in the book, whatever, something, but something clear. But don't say anything that I use just to just to gain some time. And the TAs, they do not know what we're doing. The TAs, they just grade and they do tutorials, but nowadays it's not. They don't do tutorials because you're not having in-person classes, but normally they would do TA, do tutorials. Okay, by this the conservative test theorem, uh, I can check that dy dp dy is dy, okay, is -1, and then dx. Oh, I guess this is not a no, we're not gonna apply that theorem. Sorry, it's not the conservative test here. But it's good that I did this mistake. Okay, this is not the kind of examples. But it's good, so I'll make you think a little bit. Okay. Del dx of x, which is 1, which is not equal to -1. Okay? Well, they are not equal. So I cannot apply. There are two directions of that theorem. That's why, actually. I will confuse you a little bit more. But there are two directions of that theorem. Okay? In my notes, it's two directions. Okay? But remember, I only say this direction. If this is equal, then it's conservative. But if it's not equal, it doesn't say anything. Okay, it doesn't say anything. So you cannot apply it. Well, it's the other direction. It's what we say. This is the other direction. If they are not equal, it cannot be conservative. Because if it's conservative, then it must be equal. I hope that everyone is understanding. Because you apply the theorem. If someone asks you, is it conservative? Okay, I will apply this theorem. Sorry. I will apply the theorem, and then I will realize that, what is it? Okay, I will apply this theorem, and then I realize that they are not equal. So now I apply the other direction. If they are not equal, the field cannot be conservative. Because if it's conservative, then what we have just said here, if it's conservative and they have continuous first order partial derivatives, then they must be equal, but they are not equal. So it's impossible that it is conservative. Okay, so that's the thing. This is the catch. Okay, if it's conservative, then they must be equal, but they are not equal. So let me just remove this. First, check dy and dy cubed. And they have this. Okay? Since P and Q are have continuous first order partial derivative, and we conclude that F is not conservative. Okay. Is there any question here? Okay. So there is a section on conservation of energy. But I think I will skip it because I will try to include an exercise that does not really talk about conservation of energy. Well, I'm gonna try to include it in the exercises, but there is another exercise that has an application of what we will see right now, but it has a little bit to do with conservation of energy. Not really, but it has to do with the conservation of the uh, angular momentum uh, when Earth is evolving around the sun, right? In this orbit. So yeah. So I think it's not in you. It's just physics, and apply what you know. But it's good to include it in the exercises, and I'll talk with the other instructors. So let me take a break right now, and then we'll talk about one of the first good results about line integrals, and one of the greatest ones, I think, the Green's theorem. Then we'll skip it. I think we'll just see exercises. And then we'll talk about Green's theorem afterward. Okay. And Green's theorem is a really nice, has a lot of applications in physics too, especially in electromagnetism, where you have these Maxwell laws that tells you the laws of the physics of lights, right? Because people, they realize at some point that light isn't something simple. Light is actually waves, and it's a field. Light is just a special kind of field. It's an electromagnetic field that has a special wavelength, right? The light we see, and there are many other lights we can see. Our eyes cannot see them, but they are still there. You know, microwaves and waves we use for the cell phone. Those are all the same thing. They just have the different energy. So the energy that is suitable for our eyes is the light we see. So when people, they realize that light is just an actual uh, kind of field, it's a field. It's a really three-dimensional field as we are seeing right now. Uh, they studied these fields, and they realized that these fields, they obey a certain kind of laws, and there are a couple of them. They're called Maxwell's laws of electromagnetic fields. And when you apply this, there are, I think, 4 or 5 of them, and one of them has to do with I think Green's theorem or something. So when Maxwell realized and discovered these laws, he predicted mathematically. He predicted that we can send information and laws using these equations, and then 100 years later, they created telegrams, and the first communication by light, by electromagnetic light waves. So that was the story of the TV and all of that, and cell phones. And it starts from Green's theorems. So just make sure that a little bit motivated. Okay, we'll be back in 10 minutes, in 11:16. Okay, welcome back, everyone. Green's theorem. So Green's theorem is has to do with simple curves. And I said last time, what is this? It was a simple curve. A simple curve is a simple curve without giving any formal definition. So simple curve is a curve that does not, right? So it's the only crossing point is the initial point, and that's not simple. Okay, so you have two. The first one, and then you have, okay. Consider a closed curve C, okay, with an orientation, okay. We will use the convention that the positive orientation of a simple curve Yeah, because if it's not simple, it'll be a bit hard to give this kind of definition because you go here, but right, right, a simple curve. To a single counter clockwise traversal of C. Like, I mean, this all paragraph is to say that if you have a curve that is simple, okay, we will always use the orientation of C that goes counterclockwise, which means that this is the orientation we'll always take of C. Okay? Clockwise, yeah. Traversal. Traversal. Okay? So this is because we don't want to, oh, sorry. Sorry about that. So we don't want to, because these line integrals, uh, they depend on the orientation you give to C, right? So there, let C be a positively piecewise smooth function. Yeah, so smooth, simple, closed curve in the plane. Let D be the region inside C. Let F be a vector field with continuous partial derivative. Continuous first order. Defined on an open region that contains D. Then the integral over C of the field, which is the integral over C of P dx plus Q dy, is equal to the integral over the region D of the function dx. So be careful. This is not the Yeah, VQX minus VPY dA. Okay, so basically the theorem says that if I have a curve that is smooth, and it's always in this direction, this orientation here, and if I have V, which is the inside region of, this is the inside region, okay, okay, and don't worry too much about those technicalities of open region that contains D. It means that the field is defined everywhere on D, and right, it's some kind of ball that contains D, and then I have a vector field F that is defined everywhere. Okay. Okay. So what it means is if you want to compute the line integral over the boundary of this region D, there is actually another way to do it, which is take this two variable function and just do what we were doing in the beginning, which means compute the area or compute the double integral over this region D of this function of two variables, dA. So this is Green's theorem. And you'll see it's very convenient sometimes because sometimes either this side or this side is hard to do, so you use the other side. So that's it. I mean, we will prove this theorem for some kind of reasons. But here are other notations for some other notations. Some other notations for, I mean, you can have the integral of the closed curve FD. Okay, improve. Let us see how we can use Green's theorem. Then we'll prove it. For some reasons. B. For some type. For some. Then we'll prove it. For some special cases. Okay, example. Okay. Find the area of the ellipse I mean, of course, you can do it using your what you know about integrals, double integrals, which means that you have to do probably a change of variables, do it in apply Jacobians, be much easier. The only thing is you can do it much easier. You can do a much. There is another approach, which is by applying the Green's theorem. So here's the thing. We'll choose. So we have the ellipse. Okay. And now the thing is we will put on this ellipse, or we will actually create a vector field on R2. This is on R2. We will actually create or put on this ellipse a vector field, but a very special one. Choose. So this is just choose a vector field F with P equal to -1/2y and Q equal to 1/2x. Then dx is 1/2, dy p is -1/2. So these two, they give that dxq plus dyp is equal to 1, right? Would you scroll up a bit? Yeah. To the question, yeah. So this is the question. Find the area of the ellipse, x squared over a squared. Well, a and b are in R star. A, B are not equal to 0. Thank you. Okay. So we'll choose a vector field that has this form. It's a vector field that is defined everywhere. And it has this very special property of being, this curl is equal to 1. So by Green's theorem, the integral over d, so this is the curve, C, is the curve that bounds the ellipse, C, and this is D. Okay, so what I just did here is just I took this. I took this one. It's here. So it's 1 times dA is equal to the integral over C of F dr. Let's just go there. But what is this? You're just adding. Remember what I told you about the areas. If you have a region D and you integrate the function 1, dA, it gives you the area actually of the, because you're adding just little cubes, little rectangles. Remember, we did that. We took the piece and we divided it into small rectangles and we added all of them. Then the only difference, we were evaluating a function on this subrectangle. Then we're evaluating the function 1 on this subrectangle. So what you're doing is actually you're just taking this small rectangle and multiplying by 1, which is the area of this rectangle. You can start adding all of these rectangles. So it gives you the area actually. So the area is given by this line integral. And what is this line integral? Now you do what you know. The vector field is, right? The vector field now is F is 1 over 2x y minus 1 over 2 y. And a parametric equation of C. So an ellipse is actually the same thing as a circle, but it just have kind of discrepancy between the y and the x. What is called eccentricity. So in the circle, they have the same eccentricity, I think. I think it's called eccentricity. But an ellipse has a different value on both of them, on the other side of the axis. So that's an ellipse, and the same thing. 0 to pi. So dx is minus a sinus t dt, and dy is b cos t dt. Then you apply. So a is equal to the integral of 1 over 2. Now I am on the curve, so x is equal to, oh, did I do a mistake here? It's 1 over 2. Oh, no, it's okay. 1 over 2 a cos t I mean, you have the choice, right? It's whatever you prefer. Now I'm gonna use the other one. I mean, I used to do with the scalar product. You remember, in the beginning, I did do the scalar product, right? You can do the exact same thing. I mean, you just have to write down what is r of t will be a cos t and b sine t, and then take r prime, take the scalar product, or you can do this, dx dy. and then you multiply by dy. Wait, yeah. So you have to make sure that no, I think a lot of typos on my, okay. Okay, x is this and dy. Or did I do this? It's p dx. Okay. P dx. Okay. Okay, I did a mistake here. Made a mistake. So we choose, yeah, here we go. Sorry. You need to follow me because there can be some typos. Remember, P and Q, go back to the, this is P and this is Q, okay? So you plug in, okay? So if you choose B to be minus 1/2, so you have to put it here. It's minus y, and here it's plus 1/2 x. So now I hope it's okay. Right? Okay. So now y is, what is y? It's b sine t. And what is dx? What is dx? It's minus a sine t dt plus 1/2. What is x? Is a cos of t. And what is dy? What is the, what is dy? It's b cos t dt. And then I'm integrating from 0 to 2 pi. Okay, it's not in hard, you just have to make sure you're not making any mistake. It's from 0 to 2 pi, 1/2 ab sine squared plus 1/2 ab cos squared dt, which is equal to the integral from 0 to 2 pi of 1/2 ab, which is 1/2 2 pi, which is AB times pi. Okay, so the area of an ellipse is AB pi. Okay. Okay, let's do an example, another example. Evaluate the integral So I'm trying to use as much notations as I can. Using Green's theorem, where C is a circle with center 0, 0 and radius two. Okay. Of course, when someone tells you use Green's theorem, you use Green's theorem. Okay. Okay. So here you have. Okay. So this is radius. Okay. Um, So obviously, when they tell you it's concerned, it's because this one is going to be a little bit tedious to do on the circle. So you have the radius, so you have the circle, and you have the region D, and you have the curve C. Okay, so this is P, and this is Q. Okay, the region D is given by it's a circle of radius 2. Okay, so by Green's theorem, so of course it applies all the every hypothesis you see there applies, so you don't have any problems. If you want to integrate this, it's the integral over the region D of, so as I say, this is P and this is Q. So you integrate, so it's dq dx minus dp dy, dA. Okay. So here, so this is, that's it. That's exactly what you did before. It's a double, it's a function of two variables, and it's domain D and it's a dA. So here you have to choose, how can I compute this integral? Sometimes it's better if you go to polar coordinates. So here, actually, it is better to use polar coordinate. So remember that if I have a disk, right, I need to change the variables. So it's r sine theta square minus 2 r sine theta. Now the circle goes from 0 to 2, and pi goes from 0 to 2 pi. And now the elements, the area elements is dr d theta. Okay, so if I integrate with respect to r, it's a polynomial, so it's 3 over 4 r4 sine square theta minus 2 over 3 r cubed sine theta, r between theta and r between 0 and 2 pi. Okay. Okay, so this was machinery that you have to do, and you're supposed to know how. So I'll try to do it with the curve and dx and dy. It'll be a little bit tedious, although it's possible. It's not that hard, but it's a circle, and but it'll be a bit more. Uh, the expression is a bit more complicated on one side than the other side. Okay. Um, so the thing about Green's theorem is it's not all. You can also apply it for a couple of other cases where they have holes, and that is actually a very cool thing, because that is really used in physics, especially when you want to. It gives you the value if you have a ball and you have an electric magnetic field inside the ball. The good things about Green's theorem is it can give you the value using Maxwell's laws and all of that. It can give you the value of the electromagnetic field inside the ball by, I mean, the only thing is you integrate over the ball, over the surface of the ball. In this case, it's going to be a curve. It's going to be a circle, but there's an analog of Green's theorem in 3 dimensions, which is Stokes' theorem, which will give you, well, instead of line integrals, you'll have surface integrals. And instead of the A, you'll have a volume integral. You have a triple integral. So it'll give you a connection between the surface integral and the volume integral. But in 2-dimension is the line integral and the area integral. So here we'll see how we can apply it to a couple of other cool regions. Yeah. And then we'll see how we can prove it. And then we'll talk about triple integrals actually. So let me talk about this extended Green's theorem. Extended version of Green's theorem. So if you have a curve and this is you have C2, and then you have C1, and then you have C3. Okay. And then you have D1, and you have D2, and the whole region inside is D. So well, you can apply see the thing here is here's the thing. We're gonna prove this is a quite trivial thing I'm gonna say, but it really has to do with what we'll prove. The thing is we're gonna prove the theorem for certain kind of regions, which are regions that are both type 1 and type 2. See? If D is not type 1 plus type 2, and by that I mean it is in the same time type 1 and type 2. We've seen some of these regions. They are in the same time type 1 and type 2. And D is D1 union D2. Okay, and suppose we're gonna call this type simple. Suppose D1 is simple. Suppose D1 and D2 are simple. So here's the thing, we're gonna prove the theorem for simple regions, which are both type 1 and type 2. But it's also true for other kind of regions. But what we can do for this course is type 1 and type 2. simultaneously. Um, but in some cases, even though with this very limited proof, it already applies for a lot of other regions. I mean, if you can break it down into two simple regions, you can just apply it for, you can suppose it, so we can apply our proof of Green's theorem to D1 and D2, because we will prove it for for types 1 and T2 with D1 and D2R. And what you realize is you apply it for D1 and T2, so we can apply it for D1 when we will get read the notes for this, we will get that the it's not hard. It's really just apply it for D1, and you're gonna apply it for D2, and then because of this C3 and minus C3, they're gonna cancel out, and then you will realize that the theorem is still true for the whole region, even though it's not simple. And we'll get that the integral over D1 over you will get that the integral over C1 and C2 right? This is C1 and this is C1. Okay. Now the same argument can be applied can be applied for regions. Remember, we said that the region has to be that's a catch. We said that the region doesn't have to be. I mean, the region does not have need not to be having any holes. Apply it for regions with no holes. Okay. Yeah, for regions, but really, no, that are not simply for regions that are not. But wait, for not simply connected regions. Mm-hmm. Okay, so this is a region. D. Not okay, but is it the terminology used in the book? Just want to make sure that the terminology is the same because I don't want to confuse you. Yeah, but you need to be very careful. Yeah, okay? That are not simply connected. Okay? So, but you need to be careful when you apply this. So suppose I have a region and I have a hole. Okay, so this is the region. The right definition is not really hole. The right definition is for simply connected is every loop can be, you can shrink every loop to a point, right? But so when this cannot happen, they are not simply connected continuously. So of course, if there is a hole, so that's the intuitive way to see it. If there is a hole, you cannot shrink a loop that goes around this hole. There's no way you can avoid the hole. I mean, even though unless you're gonna break the loop, which is not a continuous thing. If you break the loop, then it's no longer continuous. You're breaking the loop. So all right. So if you have this kind of regions, what you can do is you can actually do this trick here. Go here, go inside, go back, right? And then, right? Then go here, and then go inside, and then go back. And then this will give you a region D, and the region D prime. And the thing is now D and D, now D prime and D prime prime, they are simple. They're simple, simply connected because now every loop you can imagine, you can shrink it to a point, which was not the case for the union of them. I mean, if you take this loop here, you cannot really shrink it. You're gonna stick to the hole, right? So the intuitive way is to see like D prime, it has no hole, and D prime prime has no hole. So I can apply Green's theorem to each one of them. So when you apply Green's theorem to this side and this side, and then you add them, then because you did this orientation here, and then you went back and then you went backward, they're gonna cancel out. You can do the exercise, it's not that hard. It's really very, very easy. You can do the exercise and you add these line integrals, they're gonna cancel out because of the orientation here. And when you're gonna, right, but then you have to be careful. Now the new boundary that you get for this kind of regions, you have to be careful, right? So you went there in this direction. Then you went inside and then you went there, right? Because it's always positive oriented. Oh, sorry. It's always positively oriented. Uh, okay. Now let me. Okay, so you can choose whatever orientation you want, but it's just be careful, be consistent with the orientations. That's the thing. right? Right? Because if you go backward here, you're not gonna be. I mean, if you go like this, you're not gonna be able to go outside. I mean, you just have to be careful. I mean, I'm not gonna do it, but if you go like this, yeah, it'll not be one of the, the, the line integrals on d prime, because this will be the boundary of d prime, one of the boundaries of d prime. So it has to be consistent. So when you go there, that's the right thing, right? And then now it's consistent with boundary of d primes and d prime and d prime prime. I hope it's clear, but don't be confused. It's just that's the right direction to take. That's the right orientation to take. So we apply greens to d prime and d prime and obtain that the integral of d of dx cubed minus dy p dA is equal, now this one I will call it C1 and this one I'll call it C2. It's the integral of C1 px. See, so that's the new boundary. It's kind of weird boundary because you have to lift your pen if you want to go to the other side, but still it's a boundary. All right, so that's the new boundary when you have this kind of regions with holes. So let's try to do an example. Okay, it's 12:13. Um, okay, I still have one example, and unfortunately, I don't think we can prove the Green's theorem. Uh, Unfortunately, because we need to do triple integrals, and they take a little while. I don't want to be behind schedule again. So let me take a break of 10 minutes. We'll be back to 24, and then we'll do an example of this kind of regions with holes, and then I will let you read the proof. It's not a hard proof. It's really easy proof, and it's even better in my notes if you read them. It's clear and it's not empty. Okay, and that's it. And we'll talk about triple integrals after. Okay, so we'll be back at 12:24. Okay, let me go back to the example. I want to finish example. So this example is a bit long in terms of calculations. So I'm not going to do the calculations in details. I will let you do them by yourself. But the idea is to show you how you can use these tricks of avoiding certain kind of points. So for example, take the vector field okay? Evaluate evaluate the integral over C f dr for any positively oriented curve that encloses the origin. So here's the thing. For this type of problems, if you take a curve that contains the origin and you take this curve here and the domain here to be the inside of C, the problem is f is not defined as 0, right? And remember, it needed to be defined on a region that contains D, but is not defined on D. Because 0, 0 it blows up. So it's not even it's not even defined, not even talking about continuity of first partial derivatives and all that. So the trick is actually to avoid this point. Take any other curve. If you take any other curve, call it C prime. Did I call it C prime? Yeah, call it C prime, I think. Okay. Now you can apply Green's theorem to the region here, as I was saying. So now this is a region that contains a hole, yeah, but at least, and of course, the boundary is not C, It's not what I want, but you will see that for this vector field, you will see what will happen. So I'm not gonna do the calculation here. It's gonna take a long time to do. But for this very specific vector field, sorry, I'm taking some pleasure here doing this coloration. It's a bit of relaxation. It does take away the stress. It's true. I can I can I can say it. It's true. Okay. Okay. The region D now has no problem, except the fact that it has holes. But at least the vector field is defined in D, and and I can apply what I just said about the boundary, about the weird boundary that you have to go from one side to another side by lifting up your pen. But uh, I'm not gonna do the calculation, but check that, verify that dp dy is equal to dx dq. It's a long calculation. You have to do partial derivatives with a lot of x and y and simplify, and you know. So now remember the orientation of this. It was, you go on one side, but then you have to go counterclockwise. You have to go clockwise on the inside. It's a bit confusing, I know, but go back to what I said here of the orientation of the inner curve. So on one side, so the Green's theorem still applies. So on one side, it's 0. Which is 0. But on the other side, you will have still apply Green's theorem on C plus, now it's minus C prime. Now I did it because I did it because of the following reason. I mean, please be careful here. The orientation I gave here is our convention. It's counterclockwise traversal of the curve. That's always our, for simple curves, we'll go always counterclockwise. Now for the proof that the theorem, the Green's theorem, applies for this kind of regions, you have to go clockwise inside if you want to apply it properly. Otherwise, it's going to give you the wrong signs. And the reason is, go to the proof. That's the right way to go if you want to traverse properly the boundaries. So inside, it has to be clockwise. That's why I said minus C prime. So that's the right way to apply Green's theorem for these kind of regions. Please tell me if it's not clear or it's confusing. Okay, now remember that this is basically a line integral. This is basically a line integral. So this is basically C p dx plus q dy minus, because now I'm going backward on C prime, dx. And now I'm just gonna switch again to my first notations of, if I have a vector field, that is the same thing as FDR minus C prime F dr. which is 0, which means that the integral over C prime f dr is equal to the integral of f dr. And that is why I started with C prime in these orientations, because now I have the right orientations for our conventions of line integrals, right? I have my first curve, I have my first curve, and I have my second one, and now they are both having the right orientation of line integrals. Okay? So what it tells you is actually for this very specific vector field, whatever you choose, whatever curve you choose, it doesn't give you 0, not necessarily 0. If you go on a loop around 0, it's not necessarily 0, but what is sure is that it's going to give you the same answer if you choose another curve. So I mean, even though you choose some very weird curve that has very, very complicated form, and you compute the line integral, it'll give you exactly the same thing as you do it on a simpler curve. That's what we've just proved right now. So the smart thing to do is you choose the simplest curve you can imagine, compute it on that curve, and then use the fact that, okay, give me any other complicated curve, it's going to give the same answer anyway. I don't have to do it on that curve that is very complicated. So what you do is you choose the simplest one you know. What is the simplest one you know? Certainly not some very parabola followed by a line and then semicircle, and then that's going to be very, very complicated. So the simplest one you can think about is a circle. Go a circle like that. So choose C to be a circle, and even a circle, it chooses radius 1 circle. Okay. I mean, in my notes, I did A, but it doesn't depend on, you can check it. You can check that does not really depend on, you can do this. Okay, let's do it. Okay, let me just not confuse you, but you can choose any radius you want. It's gonna give you the same answer. I plus sine t, j. And now, okay, but then you have to compute because the vector field is r prime is minus sine t I plus cos t g, and now f of r t will be something that had, I think I will skip it. It's really plug in. I mean, it's 2 cos t sine t, you divide by cos t squared plus sine t squared, the whole thing square I plus sine t squared minus cos t squared, and you divide by cos t squared plus sine t squared. I think it's, yeah. Then do the scalar product and then compute. Then I'm not gonna do it, and then the integral over C of f dr, you're supposed to get something that looks like integral from 0 to 2 pi minus cos t sine square t minus cos cube t dt, and then you have to just substitute this into cos square t cos t, and then they will cancel out, and you will get the integral from 0 to 2 pi cos t dt, and good news is it's the whole thing is 0. Yeah. So for all that work to show that the line integral over every curve is 0. So for every simple curve around 0, 0. So we did it for a circle, but it's because it gives the same answer for every kind of curve that goes around 0. It's the same thing, it's a 0. Is it clear? Okay. Now, unfortunately, proof of Kruger theorem for simple regions. Please read it. Okay, because we need to move on and do the triple integrals. It's a bit fast, sorry, but it's a summer class. So it's a new chapter, I think. It's going to be triple integrals. Okay. Okay, so now we'll move to functions of 3 variables instead of 2 variables. Okay? And you will see that we will apply the exact same ideas to higher dimensional. And from this point, from the point of 3 dimensionals, there will be no we can do the same thing for 4-dimensional cubes and 5-dimensional cubes, but it'll no longer be calculus. That's not something you can call calculus. It's called analysis, abstract analysis, and it's really not something you can see, you know. But it's possible. It's possible to define integrals for an n-dimensional space, n cubes. Okay. Consider a 3-variable function. A 3 variables function and a rectangular box in R3. And this box will be called the set of elements x, y, z inside R3 such that x is between AB, y is between CD, and z is between R and S. Okay. Yeah. Okay. So we have A, we have B. So this, oh, sorry. So this is the x-axis, this is the y-axis, and this is the z-axis. And we have A, we have B, we have C, we have D, and E, and alphabets. A, B, C, A, B, C, D, R, S. Okay, so we have the cube. So what is the cube here? Uh, it's a cube that is, so it's a cube that is here. Okay. We call this B. So that's the cube. Okay. We divide B into sub boxes. B, remember, we had two indices in the two-dimensional case. Now we'll have to add another one, which is the little box xi minus 1 xi times yj minus 1 yj times zk minus 1 zk. Okay, so when you divide this into very small rectangles, and then this one into very small intervals, and then you do the same thing here, you will get a right. Okay. B. Okay. So you divide each interval into small rectangles and you get small boxes. Okay. And then you choose a point inside, call it X, I, J, K star, Y, I, J, K star, Z, I, J, K star, because now if you want to label them, you'll need three directions because you're moving inside a three-dimensional space. So you need to go on the x-axis and then on the y-axis, and then you have to go in. So if you want to label them, you need three indices. So we form the Riemann series the Riemann sum. So now you take this very specific subrectangle, you apply F to this point, and then you multiply by the little volume del with volume delta V. Okay, and then what you do next is you take the sum from I equal to 1 to n, j equal to n to l, and k 1 to m. Okay. Then when we take the limit m and l goes to infinity, we obtain, if it exists, the integral I'm just gonna repeat what I just said. Am I consistent? Yeah. Of this function here, evaluated at ajk yijk zijk times delta v. Okay. Okay. Let me just. Okay. Okay. So when f is continuous, this limit exists. Okay. And as in the case of two variables, there is a practical way to evaluate the integral, right? So instead of taking the limits, and which is not, you're never gonna be able to do that. It's very hard. Instead of taking the, I mean, it was hard for the two-dimensional case. So imagine for the three-dimensional case. So instead of taking the limit of all, we compute this in terms of M and L and take the limit, there's a practical way you want to do this. And it's Fubini's theorem, it's the same one. So Fubini's theorem works pretty much the same as in the two-dimensional case. So Fubini's theorem for triple integrals it says the following thing. It says that the integral over the box B of the function f xyz dv is actually equal to, first of all, you compute this iterated. I mean, we didn't talk like precisely as we did in the two-dimensional case. The two-dimensional case, we started with iterated integrals, and if they exist, then, well, here it's a bit faster. So if you, first of all, you fix y and z, and you consider this function of two variables. Now x is allowed to move from A to B because it's a rectangle. Once you do this, this is a function of two variables. Now you fix z, and you integrate with respect to y, and now y is allowed to move from C to D. And once you do that, now it's a function of z. Now z is allowed to move from R to S. And obviously, we're not going to keep doing this ugly parenthesis. We're just going to say that this is actually equal to the integral from A to B, C to D, R S of F Y Z dx dy, but be careful of the order here. That's gonna be the challenge actually for three-dimensional cases. It's gonna be the order, because in the two-dimensional case, you only had two, right? You only had two possible cases. It's either you start by dy and then you integrate with dx, or the other way around. Now it's going to be three factorial cases. It's going to be 6 cases, right? And each one of them has its advantage and its disadvantage depending on the example you're dealing with. Okay, so Fubini's theorem says that the integral over the box B of f x to z dv can be computed in 3 factorial different ways. For example, Now, if you want to start with dx and then dz and then dy, you can go from A to B as the integer, but now z is allowed to move from R to S, and then y goes from C to D. Is another possibility. And of course, Frobenius theorem says more than that. It says that it exists and it's equal to these iterated integrals, and all of them, whatever order you start with, it'll give you the same answer, right? Of course, I didn't include it in full details, but you want to make sure that you learn, you know what it says. You know, it's a bit fast here. It's not like theorem and all of that, but I just stated right now. The Frobenius theorem said it exists when it's continuous. You know, I didn't write Frobenius theorem if it's continuous and iterated integrals, they exist. But for our practical uses, I will just explain to you. It says that the triple integral exists and it can be computed as this iterated integral, starting by whatever you want to choose, order you want to choose, dx, dy, dz, or the other way around, dy, dx, dz. Just make sure that the border of the integration are okay, are consistent with your choice, and that's it. And okay, so I'm gonna stop here. It's 1 o'clock, and of course, next time we'll talk about regions that are not rectangles, right? And type 1 and type 2 and type 3, same thing as in two-dimensional case. And then that's it. And then we move on to spherical coordinates, which will be the analog of polar coordinates. Okay, so I will end the meeting here. Sorry. Okay, so have a nice week, everyone.